What's up? Welcome back, AP Calculus students. Today we're looking at 7.1 slope fields and Euler's method. I know it looks like Euler, but it's pronounced Euler. So we're starting Unit 7. Today we're continuing on with the ideas of anti-differentiation and finding the area under the curve, which is the accumulation, right, of whatever we're looking at. So the first thing we need to cover is what a differential equation is. I think we covered it in first semester, but it's just an equation of a derivative. So it's going to be the giveaway that we're looking at a differential equation is that we have dy dx is equal to, or y prime is equal to. All right, so let's just jump into these examples. So we're just looking to find the functions that satisfy the differential equation. So what that means is we're trying to find the y, or the antiderivative. All right, so we're trying to find the antiderivative. Which we've kind of been practicing, right? We talked about the power rule of it, where x to the n's antiderivative is x to the n plus 1 over n plus 1. So from here on out, for some of these, like the ones that don't follow the product rule, what we're going to do is we're going to be using our cheat sheet that I gave you earlier in the year. And on the back side, underneath the derivative, the derivative table is all the antiderivative tables. So I think we should have them all in here. We may not have the log based a, so we'll put that in there when we get there. Okay, so the first one, we're looking at secant squared x plus 2x plus 5. So notice this one says all functions. What that means is that because we could have, well, let's put it this way, like say we have 2 to the x, the derivative of 2 to the x is 2. And we kind of talked about this earlier. The derivative of 2x plus 10 is also 2. So notice that many functions share the same derivative, but they only vary. They only differ in the constant term. So anytime we say all functions, what we're gonna just do is this means to add a c at the end, and that's just to cover all the different constants that could be there that make the same derivative function. All right, so on secant squared, if you look on our table, the secant squared's antiderivative is going to be tangent, so this is going to be tangent x. The antiderivative of 2x is going to be, using the power rule, it would be x squared over 2, so the 2's would cancel. This would be x squared, and then any constant we have, we're just going to add an x to, plus c. Okay, so that's all we're doing. For the second one's a little bit difficult, and it gets into the chain rule stuff, which we'll cover later on in this chapter. But notice that we have this thing here, e, and we have the sign as our exponent. So this would be like the inside function of e. Also notice that the cosine is the derivative. So this is the derivative of sine t. Okay, so what that means is that we're going to do the derivative of e's itself, right? So the inside is going to stay the same, sine t. So the integral of cosine t, e to the sine t, is going to be e to the sine t. Now let's explore why that is. So remember when we were doing derivatives and we did the derivative of a function where we had an inside. So we said that u is, this would be our u, sine t. When we did the derivative of it, we had to do the chain rule, right? So we're going to go e to the sine t, because the derivative of e is itself, right? The inside stays the same, but we have to find the, we have to find the derivative of u with respect to t. And now the derivative of u with respect to t, right, this is the chain, is going to be cosine t. So if you work backwards here, the whole derivative of this thing is going to be equal to cosine t e to the sine t. So it's kind of like a big deal. We're going to spend a couple days when we actually do the chain rule. We dedicate those 2 days to chain rule. But just know that if the u are inside function and we have the derivative of that u on the outside, then we can just go backwards and do our integral. And then this outside part disappears when we get to our where is it at? So the answer for this one is just e to the sine t. Okay, so again, what we're looking for is that the outside is the inside's derivative, and when we do our antiderivative, we do it normally, and then that du, that chain part, cancels out. It disappears. All right, so for this one, we don't have a function on the bottom, I believe. So notice on the top in the derivative section, we do have this one though. It says dx a to the u is equal to a to the u ln a times u prime. Okay, so this is the first column, third one down. Now, what we're going to do is we're going to use the opposite. So notice we have this form, right? We have 5 is our a, our u is just x, so we don't have to worry about this chain, the du part, and then ln a is 5 again. So we're just working backwards here. So if this is the derivative, then a to the u is its antiderivative. So you probably want to write this down. The antiderivative of a to the u ln a u prime, remember that's just the chain part. We only use it if we have something other than x in our exponent. That's just going to be equal to the a to the u. Okay, so for this case, it's just a to the u, so it's just going to be 5 to the x. Okay, initial value problem. So it says find a particular, so it says particular solution to the equation dy dx is equal to e to the x minus 6x squared, where the graph passes through 1, 0. So the first thing we're going to do is we're going to find the antiderivative. So we're getting e to the x minus 6x squared dx. Right, so e to the x is itself, we're going to use the power rule on negative 6x squared, so that's going to be negative 6x to the third divided by 3, so that's negative 2x cubed. Then we're going to put our plus c, and we're going to say y is equal to that, right, because the antiderivative of dy dx is just y. Okay, so the second step is we're going to plug in our value. So substitute x and y. So we're going to plug in 1 for our x and 0 for our y. So 0 equals 3 to the e to the 1 minus 2 times 1 cubed plus c. So e to the 1 is e. 1 cubed is 1 times 2, so that's minus 2 plus c equals 0. And then we're going to solve for c. All right, so we're just going to subtract our e, add our 2, both sides, so that we have negative e plus 2 equals c. And then we're going to rewrite our equation with the c in there. Rewrite our equation. So y equals e to the x minus 2x cubed plus, we could do negative e plus 2 in parentheses, and that should work out fine. All right, so this is our c. So we just rewrite it with our c in there. So this one gives us a specific graph that passes through that specific point. So yeah. Now for the next one, it says find solution to f prime of x equals e to the negative x squared for f of 2 equals 3. Excuse me. Now notice this one is a little bit more complex, right? Because we have an inside function. So like we alluded to earlier, the chain rule should be in effect, but there is no outside function there. So we can't just take the derivative and call it, the antiderivative and call it good. But the cool thing about this one is that they're going to be using the fundamental theorem of calculus. Remember it said that we have an a and an x, right? So a is our starting point, our x is an unknown, and then we're going to have our function of x, which is, or sorry, we should say function of t dt is going to give us our solution. So let's go ahead and fill this stuff out. So our starting point, remember our starting point is our x. So the bottom is going to be 2. The x stays the same. Our function with t in there is going to be e to the negative t squared. And then this plus c part, we're just going to take our y here, our 3, and add 3. So this, we should say dt. This, by using the fundamental theorem of calculus, satisfies this solution thing. So for any x we have in here, we can put in our x and then find our answer. So the reason why this 3, we kind of talked about this earlier when we were doing fundamental theorem, why this 3 is in there, is because it's got to satisfy this thing, right? When we plug in 2 to our function, right, so when x is 2 here, then it's got to be equal to 3. And the cool thing about the x part is that when we plug in our x, sorry, this should be, I think my notation's wrong. It should be our dt here. So when we plug our 2 in for x on the top here, then notice the start and end point are the same, and therefore there's no area under there. So this whole thing is going to be 0, and then 0 plus 3 gives us our 3. Okay, so just a quick recap, because this is a complex one, and it's asking us to find the solution. We're using the fundamental theorem of calculus. The bottom number here is our x. This last number here is our y, and just rewrite our function with the t's in places of x. Okay, that's it for today. We're going to spend another day on this stuff, and hopefully we'll be super good at it by then. Okay, good job.